Hello again. So in this video, we're going to look at mirror plane symmetry again. We're going to take a look at some examples. Again, we're going to use this very nice figure from the online textbook by Dexter Perkins. So here, as opposed to the prior video that where we introduced the idea of mirror plane symmetry, we're using atoms as motifs. So it's a little more realistic in terms of what we would see with regard to how we think about crystals. And I'm going to give two examples here just to illustrate a very important issue. So for each of these diagrams, I've blotted out the answers here. You can go online and look them up yourself, so nothing's really a secret. But it's good to kind of work through and figure out how many mirror planes you can find. And I'll just look at the two of these right here as an example. How many mirror planes are there? Let's start with letter C. We can draw a vertical plane here and then a horizontal plane here. So with that vertical plane, these red and green dots are symmetrical about that plane. I haven't drawn it very straight. You guys could probably draw a little bit better than I can. And then with this horizontal line, I'm cutting in between these two blue atoms in the middle. And then again, the blue and the red are symmetrical on opposite sides. Then we can think about whether or not we could draw something diagonally, and I think these work as well. So how many mirror planes are there altogether, at least in two dimensions? We have 1, 2, 3. So for this guy here, we have 3 distinct mirror planes. But take a look at this arrangement over here. The arrangement is very, very similar, but the yellow atoms and the red atoms are of a different type. So here you can maybe yellow is iron and red is cobalt. It doesn't really matter what they are. If they're different atoms with different properties or different type of bonding, then we're going to have this this break in the symmetry where we can no longer draw, let's say, a horizontal line. We can't draw a horizontal line because the mirror image of the yellow on top would be yellow on the bottom. We don't have those yellow lines. So even though geometrically in terms of the pattern there's a symmetry here, it really doesn't work because we're looking at different things. If this were a real crystal and these are iron atoms, we'd be projecting it over here, then we'd want iron atoms on that side too. We might be able to draw, let's say, a vertical line. Would this work? Yeah, that would seem to work. Red projects over here and yellow projects over here. So we do have a mirror plane symmetry there. Is there anything else we can draw? Could we draw, let's say, a diagonal? Well, again, that diagonal doesn't work because even though those reds are symmetrical across from one another and the two yellow atoms are there, these red atoms over here are projecting over to yellow fellows over here, and that doesn't work. So that color coding breaks the symmetry. So we have a very similar pattern here, but it depends on what types of atoms you have. If the atoms are different and they're shown that way by this color coding, that can break the symmetry. So for this guy here, there's only one mirror plane. So I just wanted to explain that one feature. I'll let the rest of you look at this figure, either in an earlier slide in this video where it's been unadulterated by my drawing, or you can look at the online textbook by Dexter Perkins and then cover up that section here. He's going to give away the answers. See if you could figure out how many mirror planes there are in the rest of the samples there.